Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we will recall or introduce some important facts and terminology. These facts and terminology will allow us to have a better understanding of a theorem that we're going to be proving in another video. This theorem is about the estimation of sigma square, but as I said, the actual proof of the theorem will be presented in another video. But let's talk about these facts and terminology that I was mentioning, okay? So, first, this guy here is the model that we're going to be using to, that we're going to be assuming during our proof, okay? It's what we call a centered model. In another video, we have already seen that the centered model gives you the same predictions, and therefore it will give you the same residuals as the old model. And by the old model, the one that I mean is one that instead of having as the predictor, if you will, a centered version of the predictor variable, right? The old model would be one that only multiplies by xi, right? Using the plain predictor variable values, right? But we introduced this centered model because we will see in the future that it could be convenient to it could be more convenient than the regular one to study theoretical properties of least squares estimates and to find and derive formulas for confidence intervals and prediction intervals as well. Okay, we will talk about that in the future. Anyway, the epsilons, the random fluctuations, same as before. The distribution of these fluctuations are assumed to be normal with mean 0 and variance sigma square. These distributional assumptions about the error terms, that they are independent and normally distributed with these parameters, imply that the expected value of yi would be just this, right? Because the expected value of the epsilons is 0. We are only left with this, beta 0 plus beta 1 times xi minus x bar, and the variance of the yi's is going to be sigma square, variance of the epsilon terms. Make sense? Okay, something that we have seen before, but it's going to be important to remember this for that proof. Okay, another thing that we have seen before is that y bar, the sample mean, is defined as the mean, as the sum of the yi's divided by n, the number of observations. That's the sample mean. Something that you could verify later, and that's going to be useful as well for that proof, and it's going to be easy to show, is that the expected value of y bar for this kind of model, right? Expected value of y bar equals beta 0, and it isn't hard to show. Also that the expected value of y bar is going to be sigma divided by n. Again, that is not something hard to show, and it's something that in a way you have already seen in Statistics 260. Give it a shot. It's not difficult, and if you have any questions, let me know. During office hours we can talk about that. Okay, something else. We also at some point introduced this hat notation for estimates. So anyway, using our model, our estimate for the ith observation, for the yi, right, is going to be just our beta 0 plus, well, beta 0 hat plus beta 1 hat times xi minus x bar, right? Okay. Making a distinction between the actual observations and our predictions, the predictions coming from our model, is going to be important to define the residuals. Also, it can be shown that for the centered model, in general, beta hat 0 will be given by y bar. Okay, that's the estimator for the y-intercept is going to be y bar, and that beta hat 1 in general equals this, summation of xi minus x bar times yi divided by summation of xi minus x bar square, right? Now, when we derived the expected value and variance of beta 1 hat, we show that these two are the same, these quantities here. Sum of xi minus x bar times yi equals sum of xi minus x bar times yi minus y bar. Okay, so something that you could verify is that yeah, in general, these are the formulas for the least squares estimators of beta 0 and beta 1 if you are dealing with the centered model. Okay. Let me define what we mean by a residual. A residual is an estimate of an error term of an epsilon, right? So since it's an estimate, we're going to be using that hat notation, and again, it's going to be the difference between the observed value minus the predicted value. Okay, observed minus predicted. Just keep that in mind so you remember it. Okay. Now, sum of squares of the errors, or for short SSE, is defined like this, as the name suggests. It's the summation or sum of all the squared residuals. Okay. And using our notation, so we know that the residual, right, the difference is going to be the difference between the observed and the predicted values for each of our n observations, right? And then you square that. So the sum of those squared differences is what we refer to as SSE. Okay. So what we will show is that SSE, right, is a quantity that is going to help us estimate sigma square. But if you find the expected value of SSE, that turns out to be a multiple of sigma square, our target parameter. But that means that SSE by itself, it's a biased estimator of sigma square, but it's easy to fix. If we divided SSE by this coefficient, by this multiplier n minus 2, we would have automatically an unbiased estimator of sigma square, right? So we're going to be referring to that unbiased estimator of sigma square as S square. So it's the sum of squares errors, right, divided by n minus 2. You know, if we use that notation for the difference between observed and predicted, right, those epsilon hats, that's the sum square, that's the sum of square errors divided by n minus 2. Make sense? Okay, so our theorem will be this. This is the result that we will prove in our next video, okay? That an unbiased estimate of sigma square is SSE divided by n minus 2. We're going to give a proof of that result, okay? Okay, so see you soon. We're going to be doing this proof in our next theorem.